Welcome back, everybody. Let's start. Because yesterday I ran out of time, maybe I have to squeeze more even into the lecture today, because I want to quickly go through the idea of resolution, because it's one of the more powerful automatic treatment methods. But then I also want to have enough time to talk a little bit about uncertainty and vagueness. And this is, again, it's more of a refreshing and sort of giving you the main ideas. And I realized on the way here that on the last part of the lecture, there should in principle be some kind of follow-up in the curriculum, but it's one of the things of the graphical probabilistic models, which we don't have in the curriculum, which is a very active research field, very important research field. But at least you get sort of a little early taster to get an idea of what this is and how you can work with this and so forth. But I want to start with going back to what I didn't finish yesterday, and that was the most famous of all the rule-based algorithms for the classical logics, and that is resolution. It's, as I said, it's a rule-based algorithm. So we have the model searching-based ones yesterday, with the most important one, the Davis-Button procedure. And today we see the most important one of the rule-based ones, which is resolution, in particular when you go to more expressive languages. We're going to talk about that in a minute. And then there are the two topics, vagueness and uncertainty. I will tell you why, or remind you why these are different things and how you can remember that. And how people usually deal with uncertainties, and that's the main topic today, that's sort of how to represent and how to reason with uncertainty, with probabilities, something you should be aware of as well. And then the one probabilistic model that I will show you very briefly is the Bayesian networks, and sort of the more sophisticated versions of these networks are something that really is very important in AI research still these days. And then if there's time, I will spend a little bit of time explaining, preparing you for what can you expect from the exam and do the research on the project, final project. So that's the plan for today. So it is relatively full. Continued. So this is sort of the reminder of yesterday, the second half, that we have a rule system, and the rule system just takes some premises, A, and A implies B, for any A and for any B, and then you can derive that B must be true. So you have a set of premises, you have a conclusion that follow out of those, the application of those rules as a simple rewriting process, and one thing you can show is that if you apply the rule, that whatever you entail, whatever you inference, you find, you add to your knowledge base is still correct with respect to the knowledge base, so semantically entailed. And that gives you the notion of soundness of your rule. It's a correct rule. And then, in principle, you also have to show that your algorithm is complete, so that every formula that is entailed will eventually be proven by the application of your rules. So a rule set is complete then. And we've seen some of those rules. We have seen modus ponens in a differently written up way, but it's the same thing. We have two premises and a conclusion. With the end elimination, if we have if we have a conjunction, then we can conclude that either of the conjuncts is entailed and can add it to the knowledge base. We also have and introduction, so if we know that two things are true, then we can introduce the conjunction, and so forth. So there are a number of rewrite rules that are valid for our logic, and we can simply apply them. And that means that we only derive facts that are still true. So the resolution calculus is sound in that respect. So whatever we add is actually entailed by the knowledge base. But it also works the other way around, that if we apply it in propositional logic, I have to say, then it's also complete on its own. Only applying this one rule is sufficient to decide on whether a formula is entailed or not. just have to apply the resolution rule as long as I can. And I said it's complete for propositional logic. That's what I'm going to work with now. But it's even complete for first-order logic. So it means that if there is a formula that is entailed, it will eventually be proven to be true. The only problem is that the algorithm might not terminate. So that we might have to wait forever and still not know whether our formula is entailed or not, which makes it a semi-decision procedure for a semi-decidable calculus. So the only thing that you can decide for sure, because we don't have determination, is unsatisfiability. So we can prove that if we have a knowledge base, we transform it in closed normal form, we run resolution, we know that if it stops, that that we find a contradiction, then I know that the formula has been unsatisfiable. That's the only thing you can do with resolution. Of course, we can apply the trick again of adding the negated conclusion that we want to prove, and then we have our proof by refutation again, and so we can show entailment as well, applying this rewrite first. So the resolution algorithm that you usually apply is as follows. If you want to prove entailment, you convert it into a conjunction of the knowledge base plus the negated assumption, and you translate it into closed normal form, and then you apply the resolution rule to get more clauses, new clauses. And to all the clauses, the ones that you had before, and the new ones, you apply the resolution rule again and again and again and again. It's just one rule that you apply until you either have no clauses that you can add anymore, but you haven't found a contradiction, and then the formula is not entailed because you found out that it is satisfiable, or you find a contradiction, you know that the formula is unsatisfiable, so that the entailment is true. And how do you find the contradiction, as I called it? The contradiction in resolution is what's called an empty clause. And that comes basically out of the understanding that in a formula in closed normal form, each of the clauses, so A or B, whatever you have, and C or D, each of those clauses are somehow constraints that have to be fulfilled conjunctively, as we said. So either one of the two is true, or one of those two is true, or one of those two is true. Yeah? So we saw yesterday with the Davis-Putnam that if we have a clause with only one, so a unit literal, then we know exactly that this one has to be true, otherwise we won't find a so that's sort of a unary disjunction. So it's A or, so no or. But now there is even the case where we have no option. So we have no A here. We just have an empty constraint. And this empty constraint means that it's always impossible to satisfy it. So here we satisfy our constraint by just getting A true. But if we have an empty clause, an empty constraint, we can never make it true. So the algorithm of resolution is the search algorithm to find an empty clause. A clause which has no satisfiable disjunctions anymore, literals in the disjunction. So this is the algorithm. If you want to show unsatisfiability of this knowledge base plus the negated assumption, then you build a set of clauses in closed normal form, and then you loop. And for each pair of clauses in the set, you apply the resolution rule between those two, and you add the new resolvent to your database. If the resolvents contain the empty clause, then you return true, which means you return true in the sense that your entailment is true. So it's unsatisfiable, so the entailment is true. And otherwise, you just add it to the set of clauses you have, and you loop. And the rules that you apply, the one rule, but in three different disguises, so to speak. There is a standard resolution rule which you can use to remember the rule itself. If you have a literal that occurs in two different clauses, one way negative and one way positive, so once with a negation and once without a negation, then you can construct a new clause that contains the left-hand side disjunct and the right-hand side disjunct, and you can just stripe away the literal that you are doing the resolution of. So you pick one propositional variable that occurs positively and negatively in two different clauses. You delete it and you add the remaining disjuncts together. I have to check, but I think I have the example down here. So if you have A or B, and if you have not B or C, then you can add A or C. Yeah, that's the rule. It's very, very simple. And it's the only rule that you need in order to have a sound and complete algorithm for propositional logic if you apply the algorithm that I showed on the slide before. So that's the main computational tool that you have here. There are some improvements on it. But for example, if you use a literal that occurs only once, so the unit rule we applied in Davis-Putnam. Here we apply the unit resolution rule. Always go for the one first. If you have a contradiction between one literal in this set and a single unit literal, a single clause, a unit clause, then you can easily simply take out this li and keep all the other literals in your clause. Yeah?
Just jump back to that example you showed where it collapsed A and C.
This one?
Yeah, so conceptually I understand what you mean, like B is going to be one of the states, so therefore I don't care about it, I only care about A or C. But if I get A and it was the B that I got, because it was going to be one of the two states, then I've satisfied the left side, but I haven't satisfied the right side. So how can I collapse them down?
I don't think I understand the question. So this is the set. This is the set of clauses. So this is the first clause, this is the second clause, and we have them conjunctively. So these two things must be satisfied.
Yep.
So suppose that we have B satisfied, then this clause is satisfied, the top one, and we need C. Yeah? So if B is true, then C must be true. If B is false, then A must be true.
So that's why I know it collapses down to A and C, but we don't know what state B is going to be. What happens if I had a situation where B was true and A was true?
It would still, you keep those clauses. You don't delete anything, you keep those clauses.
Yeah.
So as soon as you know that B is false, you will, so if I now add the information that B is false, then I can apply resolution again, and I derive that A is true. A must hold. So I add the new clause A. But even without knowing whether B is true or false, I can already derive that this must be entailed, so that this should follow from the resolution rule. Yeah? Okay, so it just adds new information, and without knowing what B is, I can already, because of this reason, I can already derive that C or A must be true. And this is simply by applying this rule. And then there are more, so you can have a full resolution rule where you can look at all the contradictory elements. So you have an n-ary clause and an m-ary clause. Here are k, clause of length k, and clause of length n. And you just look at the literals that are contradictory, and you add everything that is not these two literals. So here's an example. So this is the formula we had from the Wumpers word. These conditions. So we have The question is whether if P11 is equivalent to either P12 or P21, and we know that that P11 is not true. Can we derive that not P12? So is there a pit in P12 or not? And remember, we translated that yesterday into closed normal form, and this is the closed normal form. So this is equivalent to these five clauses. So not P21 or B11 is the first clause, not B11 or P12 or P21 is the second clause, and so forth. And the last one is the negated assumption. Yeah, is that clear? So remember from yesterday. And now we can combine pairs of those clauses that we know in order to derive new facts. And the goal is to derive a clause that is empty. Let's see how that works. So if we combine this clause, not P21 or B11, with this one, then we have a negation between the literal here and this literal. So what can we derive? Just have to follow these two lines. I'm not sure whether you can see that. So if you combine this and this, then you end up in this new clause, namely not P21. If you combine this one and this one, then we have a contradiction between P12 here and not P12 here. So we can derive a new clause that has this element, not this one, but this one, and this one. So not B11, P12, and B11. So I think I've meant this one. So here we have it. So if you do that systematically, if you look for all the possible clauses where you have a contradiction literal in it, you can derive new things, and you just add them naively to your database. So we have added this one as a resolvent between these two. We have added this one as a resolvent between these two. And you always have to look in the example on which literal did you apply the resolution rule. So here, if you want this one, I think it's between those two. So we have the contradiction between B1. B1 is here positive and it's here negative. It's a negation here. So we take the not 2, 1 is here. We have the P12 here, and we have the P21 here. Yeah. And then we yeah.
Can you compare it with the two contradictions? Can you never move to
there is some extension of this this rule, but it's a little bit more complicated. So for us, let's just keep it with one single literal and apply the rule. And then basically you end up with more clauses. So we've now extended the set of clauses. And we find here a clause which says not P12, and we have the original clause P12. And now comes the trick that if we apply the rule of resolution here, we add everything of this clause apart from the one that is resolved away, which is nothing. And we add everything from this one, which is not resolved, which is also nothing. So we construct a new clause that's empty. And the moment that we constructed a clause that is empty, this basically means that we have constructed a constraint that is impossible to satisfy. And at that moment we can stop because we found a contradiction. So in a way, it's a sort of completely different paradigm to the searching for a model, because if you haven't searched in the model search, you can always do the backtracking. But here we have complete constraints. So if one of those constraints is impossible, we know already that my formula is unsatisfiable. And the empty clause is also always the one that gives you this impossible to satisfy character. And what this all burns down to is again a search procedure. Now the search procedure is the state space representation of this problem would be that we have a number of clauses, the beginning state of the set of clauses, and we want to produce new clauses by applying the resolution rule. There's only one rule we can apply, so that's easy at least, but we can apply it on all the clauses in our set, so on the power set of all the subsets of size 2. So we have to go through these lists and search for all the transitions that are possible and all the combinations of literals that are contradictory in 2 different clauses. So, and then you decide on resolving on R, for example, and you get a new thing. And then you have to decide which one to resolve on. You resolve on P in this case. You resolve on a new one up to the point where you find a contradiction. So again, the same idea that you have some systematic representation of the transitions from one state to the other in the application of the rule, and the goal is to find as quickly as possible this empty clause. And so there is little advantage of doing this in propositional logic, because it's slightly too powerful and it isn't directed enough in search. But the nice thing about this algorithm is that it's easy to extend to first order logic. And in principle, it follows the idea that I talked about on Tuesday about the propositionalization. When you have an extension quantifier, you introduce a new constant, and you can therefore translate all your formula as well into those grounded clauses. And on that very expressive language, we can then still apply the same resolution rule with some more tricks and so forth. And this has become one of I think, the most powerful reasoning methods for first order logic, resolution on this principle, but slightly extended to deal with the variables in the language. So resolution on itself, you don't really need for propositional logic, and therefore we also focus in the exam on Davis-Putnam. You don't have to do this in the exam, but you should be aware that this is really the way to go if you want to go to more expressive languages such as first order logic. So let me summarize. I've tried to define what logic is, why this is relevant for intelligent agents. We looked a little bit into how to model with these languages, in particular in the context of the games. And then, for me, the most interesting general part was how can we do the reasoning, so the automated reasoning, the computational part of logics. How can we decide by some algorithm whether a formula is entailed or not from a knowledge base. And the rest of today, I want to sort of deal with uncertainty and vagueness. And obviously, the problem is that everything we've done so far assumes some kind of certainty and crispness of the information that we have. So I can model that it is raining, but the question is, how hard is it raining? So if I say it's raining hard outside, then this is with a certain probability, a certain uncertainty in this, because I don't really know what it was raining 5 minutes ago when I came over. It's probably also still raining now, but there is this element of uncertainty. And there is the vagueness of it's raining hard. What do I mean by it's raining hard? So for someone who lives in the Sahara, every little bit of rain for the Icelandic person in the room would probably be a very heavy rain. And these kind of different understandings of these terms, these propositions is possible because we are now in the real world have to deal with uncertainty and vagueness. And this comes from underspecification. Sometimes we don't have enough information. Very often it's incomplete. So think of our Schnapsen game, we simply have incomplete information, so we have to somehow deal with the probability of our opponent having a certain card on its hand, if we don't want to do it fully. Often you have measurements that are unreliable, that are rounded off, that are not comparable, and so forth, and they are not crisp. Or if they are crisp, they might even be too crisp, so if you have too much information. So all these imperfections mean that the logic itself might be very useful for the reasoning process, but not always workable. So just to make sure we have our vocabulary clear here, so what is the difference between uncertainty and vagueness? So if I have a sort of the glass is 50% full, then in principle, this is, I think, relatively clearly to be understood to be more on this side. So we have a glass, and it's we have the half of the glass is water in. But the weather example might even be better, where outside I don't know, I don't have enough information. So here the chance that the glass is full, and that's what this term might sort of confuse you, the chance that the glass is full is 50%. So half of the chance of half is half that the glass is full. And this is the this is the sort of vagueness of the information. Nobody will check whether it's really 0.5 liters in the glass. And the question that you don't know whether the glass is full or not, that is one which has to do with us not being able to know. So that's the uncertainty. And I'm trying to get through the notion of vagueness because I think it's the one that is less important than the uncertainty before the break. And then the second half we'll have a sort of reminder of probability theory for you to, yeah.
Still didn't quite get that distinction. So uncertainty, you definitely never know, whereas vagueness, you could know that in this situation there's enough information to know. I didn't quite get the distinction between vagueness and uncertainty.
So in uncertainty, the glass is in a certain state, but I don't have enough information to say in which state it is. Whereas here, I have exactly the amount, I know exactly, I can observe, I can measure, but still it's more useful to model this as it's half full, rather than it's 50.0001 full and 49.996% empty. So this adding of specific information in this case doesn't really help us. So we are very good at dealing with this approximate logic. It's a fuzzy logic, and that's what I'm getting at now. So so here is the word. So so the model theory that I described for the propositional logic was based on the notion of truth. So a certain formula being true or false, and an atom being true or false. But there is an alternative way of looking at this if you have a predicate, that that an object could be either in the predicate or not. So you could also define a predicate, a unary predicate I'm talking about, as in terms of a set. As propositional logic are unary predicates, I could have also given you an alternative semantics in terms of an element being in a set. So the set of all situation where it rains, the set of all full glasses, the set of all teachers, the set of all students, and so forth. And that would still have been a crisp definition. But there are sets where this definition is not as crisp anymore. And so there has been the notion of fuzzy set theory, and on the basis of, and this is a very nice formalism to also deal with uncertain terms and to do logical reasoning over it. So the definition that you would give, for example, a set of tall men could be someone who has a length of more than 190, and that would then again be a crisp definition. But it would not really cover the notion of the term tall. So in fuzzy set theory, you are allowed to have certain objects being a member of a set to a certain degree. And it's this mathematical approach that we use in order to model this notion of vagueness. What we want in the end is a fuzzy logic, so a language that we can do reasoning over when it is defined in these terms of fuzzy sets. And here's the definition of this language. It's a simple propositional language as it was before. So we have the propositional syntax. You wouldn't distinguish the language itself from the language of propositional logic. But now we interpret the values differently. So in the crisp case, we say that the interpretation of the value is either, yes, it is in the set, or it's not in the set. But in a fuzzy way, we can also assign some kind of value between 0 and 1 to it. So someone who is 2 meter 25 will really get the value 99999%, 0.999 of being in the set of tall people. Someone with 1.80 meter, it's already more difficult. So is that a tall man? In the Netherlands, it's different. So you can give touch a number of degree to which it belongs to this set to the individual objects in your set. And then you can extend this semantics. So now we don't assign true or false anymore, but we assign a value between 0 and 1. And then we can extend this by the following operators. So first I assign a fuzzy value to the individual propositions. And then if I have a negation in front of an operator, then I just calculate the value of this negated value as 1 minus the interpretation of this atom. If I have a disjunction, I just take the max of the two values. If I have a conjunction, I take the minimum of the two values. And if I have an implication, I have this min between 1 or this value 1 minus VA plus VB. Yeah? So each of those operators gives me, given the input of some number, recursively allows me to calculate the value to a formula, a fuzzy value of a complex formula. And this is something I want you to do in the working group tomorrow. Just take a formula, assign some basic values to your propositions, and then calculate the value of a complicated propositional fuzzy formula. That's in principle all I want you to know in the exam. Sorry guys, it's incredibly easy. I hear almost every word you speak. I don't know whether that's for the rest of the group as well. But the acoustic here is horrible because you're better to understand, I think, than me. So be a bit careful what you say. So the fuzzy logic has a stronger big brother, and that's fuzzy set theory. And that is sort of very similar, but now we talk about the sets themselves in our language, and we use a classical set of operators such as conjunction and disjunction and so forth. And again, we assign to a certain member, certain variable, we assign a value in the sense of a membership function to a certain degree. So the interpretation of this x, this object x and y, is now that A holds, for this A in the function, A holds to a certain degree y for object x. And then we can reduce this to classical set theory for values where I'm completely 100% certain I give the value 1. If I'm completely if I'm certain that it's a member, then I give it a value 1. If I'm sure that it's not a member, then I give it the value 0. And then we basically have classical set theory. And it's interesting when we have some notion of degree of membership. So then you get as input your values, and your function gives you some degree of membership to this class. So if this is the fuzzy set of tall men, then you get these kind of representation curves where you represent. So that would be your representation of what you think tall men are, or what is the characteristics of tall men. It's often written in some kind of linearized form in order to make it easier to calculate with. So steps of linear functions. And then there are different types of these functions, these fuzzy functions. So this is an increasing function. You start with very unlikely, and then you have some sort of normal, almost linear increase, and then you derive some top here. And examples are tall, old, heavy, long. Of course, if you have sort of more average-like functions you want to model, so the medium-sized car or the near Amsterdam cities, then you have a different kind of shape for your function to work with, where you have the peak somewhere in the middle and the distance. If the distance becomes smaller again, then or the size of the car could be either too small, and that would be on this end, or too large, and that would be on this end for a medium car. Then there is more you can say. You can have operators that operate on the language itself, where you say, if I have my tall Dutch man, then you could have a sort of an operator on this and say, okay, now I want the very tall man, and that in principle should just modify the shape of your fuzzy function, and in this sense it sort of moves the hedge that it moves the function in one or the other direction. So these are then things that you can do with your fuzzy sets. And obviously, you can also apply the classical set theoretic operators given those definitions, and that gives you the same idea here. So if you have a union, there was a disjunction before, you just take the maximum. If you have the intersection, which corresponds to the conjunction, then you take the minimum. And if you have a subset relation, then you take this definition. And if you have values 1 and 0 only, then this all reduces to classic set theory. But if you have modeled your atoms as fuzzy functions, then you can calculate them this way. Yeah?
What does crisp mean?
Crisp means not fuzzy.
So.
Yeah, it's just the opposite of fuzzy. Yeah? Which one? The subset formula. So the definition of subset here, as it's given, as far as I understand, is that whatever element you take of your one set, it must have a higher degree of being to this in this set than of being in the other set, and then it's a subset. But I have I don't know more about this than explaining how this works. Why this is the best way of modeling subsets is something we would have to look into depth, where we don't have to. But that's a sort of one way of defining subsets which apparently work. And it's, I know that there are many different definitions for other operators. So implication, for example, has been discussed. What is the best definition of implication in fuzzy logics? It could be that this has also has a longer literature. I wouldn't know about it. It's also said here, so instead of using the minimum, you could also use the product of two values. So you would combine the fuzziness in this definition here. It's a relatively strict one. You take the maximum or the minimum. So if you have two fuzzy functions and you combine them using the union, then basically you always take the maximum. So that would be the beginning line here, and then the red line to here, and then the blue one again to here, and you would get this shape. So you modify the shape of your function by combining functions, fuzzy functions. And the same would be for the intersection, where you take the minimum. So you start from down here, and you go down again, so this is this bit, and then you go up until you go down again. So it's just a combination of two functions by the set operators in fuzzy logic. And then when you look in the fuzzy, not only the subclass and class relations, you can obviously also define relations between objects. So up to now we have looked at things like tall, low, wet, feverish, but we can also combine those things between multiple objects. So the classical definition of relation. And there you have the notion of composition. So in classical logic, not in compositional logic, there doesn't exist. The first one is also, I'm not sure whether it's possible, but there are logics which explicitly allow you to reason over relations between objects. And the composition is one of the things that's very useful in the information science students and AI students have seen it in knowledge and data, that on web modeling and object modeling, it's very useful also to be able to model something as the uncle being defined in the terms of being the brother of the father or brother of the parent or something like this, so that you don't have to explicitly state all this. So the definition of this composition operator is that you go have a relation as a subset of the Cartesian product between the two sets. So in this case, the composition between R and S is defined as now the Cartesian product between X and the Z here. And it basically means that X and Z are in the relation of the composition. This is this here. If and only if there exists something that's in the middle, intermediate object, that is in an R relation with X, and that is in an S relation with Z. So in principle, that would be the definition of two people being in an uncle relation if there is something that is apparent, so that R would be the parent relation, and then this thing, this Y, is in a brother relation to this object that I'm the uncle of. And I think I might have sort of confused the uncle, what is an uncle now, but I hope that the idea is clear. And in fuzzy relation now, you want to extend that to fuzzy relation, and here the definition is just that you take the maximum or the minimum values that you have between in the relations between objects. And here is an example. If I have a relation X is much larger than Y, and a second relation which is Y is close to Z, and I want to define a relation that says that X is much larger than something close to Z, then I somehow want to combine those values, those functions. So if I look at this representation of the relations between X and Y, then 1 is obviously not much larger than anything. 2 is a little bit much larger than 1. 3 is already quite some more large than 1. 4, of course, is absolutely, and so forth, and that's where you get these values from. Yeah, and that's a representation of the notion of being much larger than. And this is the same, there is a sort of 1 is obviously very close to 1, and so forth. And then you just have to calculate the minimum values between those two, and just pick the minimum values here, and then you take the maximum to calculate the this value of X that is much larger than numbers close to Z, the composition of these two operators. And this is mostly in our framework of intelligent agents, mostly used to really have model relatively simple rules in relatively simple agents, in which you want to have this kind of fuzzy control where you give rough fuzzy definitions of the properties that you want your agent to achieve, and then have a simple translation into such a formal system. And before we have a break, let me summarize the properties of the fuzzy set theory. It's very flexible. It has also a very nice theory that coincides with the theory of the normal standard set theory, if you take the extreme cases. And it's been really successful in many practical applications. The question, of course, is where do you get your fuzzy theories from, the fuzzy functions from? So I now sort of draw you, magically, some kind of function on the board but you have to sort of make a decision of where this comes from if you want to take it as input for your agent. So you can learn that, you can measure that, you can use experience for it, but it is not very clear where those values come from. And it's the dominant approach to vagueness, and that's in principle all I wanted you to see, or we have time to get into. It's important for AI systems, for intelligent agents, to be aware of this impreciseness and the vagueness, and how to deal with that. And this is a short overview of some of the formal methods that you can use here. So I apologize for running over time, but can we still make it back at 12 so that I can finish my second half?